terms of material and the pace we're going, we're in decent shape, even though I was sick last week, or the week before last. But I'll show you what I've added to D2L. It's basically 4 new things. And we can go over them, it's just a review. And then I'm also going to push our test back instead of, I guess it still says Friday online. I meant to at least move that to Monday, but I'll probably move it to Wednesday. And like I said, that'll put us in just about the right spot to have about 1 more month to finish out what we should. I also need to get a look at that ACS final and decide what to focus on at this point, or whether I'm going to go back to those ice tables or not. But this, so let's just review today a little bit, and then, Wednesday, I'm not planning to do the lab, so we can just lecture, because again, we're behind a little. We have a new lab that we were going to do this week, but I figured, and it was kind of optional that we do it or not. And I wasn't going to do it, but because I was sick, I decided not to. So we say next Wednesday. And I'll change that on the schedule. That's what I'm switching it to. And I will cover, I'll do more in chapter 14. And well, it's definitely going to do pH and POH, polyprotic acids, acid-base titrations, hydrolysis maybe, and then a little bit of chapter 15. And I think that'll put us in good shape to cruise towards the end. It's all this stuff at the end of the chapter, at the end of this book, that I need to see what of this is really. Thermodynamics is not a big thing in introductory chemistry, so we'll probably skip that chapter altogether. But like I said, I'm going to look at that ACS one. And I'll decide, we're really going to pick and choose what we do for these last few chapters, is what I'm saying. But we're going to do almost all of 14, almost all of 15. And then I'll have to figure out what we do from there. But the thing, as usual, to focus on is what's on D2L. We can review some of the chapter 13 stuff if we want, but we have gone over this chapter 14 stuff, and this is the only thing I managed to accomplish over break. But let's look at these. So this is name the conjugate acids. I can tell by these numbers over here, not a lot of people have practiced these, but now is the time to start looking at all of these. So 12 people work on this one, 10 people work on this one, etc. But you should start looking at these, because I am going to do a bit more before we get to the test. All right, can you tell me what the conjugate acid of this is? Question 1, and name the conjugate acids. If I say what is the conjugate acid, I'm saying that OH is the base. That's a base. If you consider that a base, what's its conjugate acid? Huh? No. Yes, it's H2O. Somebody said H+. If you've got a base and you're trying to figure out what the conjugate acid is, you can think in terms of H+. You know, what's that going to do? Well, this OH minus and this H plus, when you put them together, you're going to have H2O. So that should be the answer now. Going the other way, if you consider this the acid and you say, what's the conjugate base? You picture this with an H plus removed, and then that would be the conjugate base. That should be the answer there. Question 3. You may or may not recognize a lot of these, but they're from polyatomic ions show up a lot in acid base. All right, what is the conjugate acid of this? If you just think in terms of that, what you put here is going to be the conjugate acid. And do notice that a negative and a positive, once you put those together, this will be neutral.
How do you know where you're putting that and find where?
Since I do this A, B, C, D, E, you should be able to see it there. But when you do an acid base, you tend to stick the H on the front.
So how do you know which side, how to write it out in this
Well, the difference between the acid and the base is the presence or absence of an H plus. You follow that?
Yeah, but what does that have to do with conjugate acid?
This is the base. This is the acid. And these are conjugates of each other. Conjugates. If it's a conjugate acid-base pair, the difference is the presence or absence of that H plus. When you have the H plus on it, it's the acid. And when you remove that H plus, it's the base.
You're just using A plus to neutralize the charge.
Sort of, but you can have this to be neutral and this be positive. In some cases. Like, well, OH wasn't an example. Here's another one. This is probably in there. What's the conjugate acid of this? H3O.
So you're just adding one more H plus.
Yeah. Do think of it as an H plus, though, because in this case it made this positive.
But so it'll always be just adding one more H plus.
Yes. Going from the base to the acid, and it's the opposite process going in. You remove an H plus, and just do pay attention to what that does to the charge. Conjugate acid of NH3, which is neutral. If NH3 is a base, and I should be saying Bronsted-Lowry acid bases, because that's the definition of Bronsted-Lowry acid bases, is the presence and absence of the H plus. So if that's a base, what is the acid? There you go. And do pay attention to the plus, because that one plus makes this positive. I have some more in here.
So whenever you add hydrogen, the charge is going to be positive and neutral?
Well, you pay attention to the charge on both of them. In this case, you got a negative here and one negative here, one positive here. Once those come together, it'll make this neutral.
What if you have two positives?
If this was, well, doing this, you would add two of these. But when you do acid-base conjugates, you're only one step away. You're not going to add two H pluses to something. But if you had something that was 2 minus, like, if I had SO4 2 minus, and I said, okay, what's the conjugate acid of that? You're going to go, each SO4. This one positive eliminates one of these negatives, and you still have one negative left.
Because I was looking at question that H5 and 2 plus.
Is that in this? What number is it?
8.
Okay.
I think it was 8.
Okay. Just look at it. Yeah. So if you add an H plus to this, so this is number 8, H5 into. That one's a little exotic, but I included it because there was an example there. H5N2 is a negative. So if you're asking, no, it's positive. If you're asking what,
Like, would it be H6 N2 2 plus or H6 N2 minus?
2 plus.
Because you just have a positive and a negative.
Is that just plus? Oh, it's 2. Okay, it does end up being 2 plus. Because you've got a plus here and a plus here. Once you bring them together, you're going to have 2 plus. So then you'll have H6, 2 plus. So that's what I mean. Do pay attention to the charges. You're adding an H plus to it. So note what that does to the charge. I guess I meant to go back and do, what is the conjugate base of some of these things?
How would you do the base?
Exactly the opposite of what we're doing now. If I said, what is the conjugate base? Better eraser. It went away over. Okay, if I ask for the conjugate base of this, then you think of this as the acid. Do you know what the conjugate base of this is?
Would it be SO4 minus 1?
Almost. This is already minus 1.
Oh, minus 2.
Yes. So you're thinking like this. Does that make sense?
Thank you.
I should add some of these to the show.
For the temperature prediction direction and the pressure prediction direction for chapter 1, are you going to add the reverses of those, or are you not going to use it?
Oh yeah, I need to add reversals of those too. I'll make a note of that. I think it's obvious without doing that. I'll make myself a note, so I just can't make it a priority. This one was named the conjugate.
And then I think you have to make the conjugate basis for the
I thought I did. Oh, name the conjugate base. Okay, yeah. I made it a separate thing. I might have reused it. Yeah, that's a good question. So in this case, what is the conjugate base? What is the conjugate base of OH? And what is the conjugate base here?
OH. Oh, no.
If we consider this the acid this time,
O2 minus?
yes. O2 minus. So if we consider the acid here, and this is the base, and those are conjugates. This is what we just did before. If we consider this the base, and I want to come up with the acid. Does that make sense? Here we're considering this an acid, this would be its base. Here we're considering it a base, this would be its conjugate acid. Does that make sense? Yeah, I think I just used a lot of the same on-off words. what about this one? H5N2 plus. What is the conjugate base? So if this is an acid, what is the base? H4N2. Let's do. So since an H plus comes off, that's where that positive goes. That tells you that this will be neutral. See what I mean about the charge? And what we did before, if that's a base, does it make sense? Conjugates for the Bronsted-Lowry definition, the difference is always going to be the presence or absence of the H plus. Okay, conjugate acid-base pairs, again, same idea. In this equation, is this an acid or a base? It's an acid because over here it has lost that H plus. So this is an acid. And its conjugate base is these two are conjugates. Okay, the other acid-base conjugates that are here, these are going to be conjugates, but which one's the acid and which one's the base? Say again? Yes. So this one has an H plus that this one does not have. So in that case, those
So the base is on the right?
Here we have an acid reacting with a base, as in an acid-base reaction. Two acids aren't going to react with each
So
other.
acid and the conjugate base go together?
Well, this is the acid, and this is its conjugate base. This is the base, and this is its conjugate acid. This can also act as a acid if it loses an H plus. But in this case, it's behaving as a base, and this is its conjugate acid. Okay. What about this one? If we call it A, B, C, D, and E, what's the answer to this one? It's easiest to identify something first, though. Is C in here acting as an acid or a base across this reaction? What is it? A base. It's accepting an H plus. So Cn is a base here. So I would start by looking here. Cn is not. Okay, what's H2O behaving as here? The difference between the H2O and the OH is the presence of an H plus. So H2O is an acid here, and OH is its conjugate base. So Bronsted-Lowry acid is H2O, its conjugate base is OH negative. This one's wrong though, because it's calling the HCN base. CN's the base. I think it's this one. Again, I do these algorithmically, so if you see any problems. You see that? You see why that's the right answer?
Can you go to question 6?
Huh?
Can you go to question 6?
In here? Oh, yeah. I know these are crazy to look at, these hydrates. Here though, look at, so you've got copper, you've got H2O there, and you've got a 3. So that's telling you you've got 3 H2Os connected to a copper. It's called a hydrate. These are coordinate covalent compounds that we don't talk much about. But notice if I can add an H plus to this whole thing, this OH will become another H2O, and then I'll have CuH2O4. You see what I'm saying? If I added it, so all of this in brackets is one thing, one complex altogether. So I'll say that first. And then notice you've got an OH here. If you can add an H plus to all of this, you would turn that OH into another H2O. So then you would have CuH2O4 instead of 3. You see that? What's on the other side? Well, yeah, that's exactly what we have right here. So you have CuH2O4 here. So this is accepting an H plus. And over here, it has accepted an H plus. You see that? So that means this is acting like a base. Because on one side of the equation, it accepts an H plus. You guys see that?
So all you have to do really is look at the charges.
Maybe I should include one of these on the test just because that makes it look so complex. But I wouldn't say you're just looking at the charges. Yeah, I suppose that works because you're adding a plus to this, so it's going to become 2 plus. And you're removing the plus from here, so it becomes, instead of plus 3, it becomes plus 2. So maybe that works.
So do you just pick the one with the most hydrogen if there's 2 hydrogens in the...
No, I think what he said is probably the best strategy. The copper complex here is a 1 plus, and over here the copper complex has become 2 plus. So it's obviously gained a plus, so it's gained that H plus. You see that?
So if it gains it, it's the base.
If it gains an H plus across the arrow, then yeah, it's a base on the left side and it's an acid on the right side. That one's just complex because we haven't talked much about that type of. This is number 6. I want to put it on a test and force you guys to look at it because they like doing that type of thing on the standardized tests, giving you this sort of complicated. I think that there. It's easy to look at from this. Put it this way, if you can do all of them in here, it's exactly the same concept as this one. Let me point out again. The copper complex here says H2O3, It also has this OH here. If you add an H plus here, then you're just going to include one more H2O, so it'll be H2O4. You guys see that? You don't like to think about that, but I can tell. So this one is the base. CO4 is the acid. That one just looks complex because it's a, do you understand the other ones? The other ones don't have those complexes.
Are you gonna go over number 10 and 11?
Absolutely. Alright, this one, and okay. So you see sulfur here, right? And then you see sulfur here. What's the difference between this sulfur compound and this sulfur? This one has an extra H. So that one's the acid. And this one's the base that accepted that H plus. So there's your conjugates. You can do the other two, the H2O and the OH. H2O is the acid here, OH is the base here. Alright, so for 11 you see the PO4. You have PO4 on the left and PO4 on the right. The difference is the PO4 on the left has two H's on it, and PO4 on the right has one H on it.
So the H2PO is the base?
It's giving up an H plus between here and here. You have to think about what's happening across the arrow. It has two H's on it on the left and only one H on it on the right. Acids are the ones that give up an H plus. Bases are the ones that accept an H plus. So on the left side it's an acid. On the right side it's this conjugate base. That makes sense?
There's not an option for it to H2PO be the acid.
BLS is H2O4, it's kind of
Wait, in mine is
is the first one. Bronsted-Lowry acid is the H2O. Do you remember what amphiprotic means? That just means it can behave as an acid or a base. You give up an H plus or it can lose an H plus. All right, NH3. As long as there's an H there that it can give up, it can be an acid. So this one, it can give up an H3, H plus, and it can accept an H plus to be an H4. So,
how do you know if it's not
if it has an H on it, then it can give up that H3 and H plus. At least for the example I'm giving you, it's true. You see that it's got NH3 there, so it can give up an H. And NH3, this is question 1. NH3 can do this. So there it is acting like an acid. And it can also do this. say it again.
Is there characteristics of that bottom one from the PLA?
That's behaving as an acid and that's behaving as a base. Should be that.
So if there's no hydrogen in the original, like, then it's not.
This one has a hydrogen it can give up. So it'll become PO4 3 minus. But look at this one. It's cases like this one, number 3. This one can't give up an H plus. It can accept an H plus and behave like a base, but it can't give up an H plus to behave like an acid. So that one's not amphiprotic. I should put the synonym on here, amphoteric. Okay. This one can definitely give up an H plus. Let me remind you something about NH3. This is NH3. And if an H plus comes along, a positive charge jumps on that pair of electrons. Notice there's no pair of electrons here, there's no single electron here. That's the Lewis structure of hydrogen with one electron on it. You remove that electron, that's how you get the H plus. There's no electrons there. That pair of electrons becomes the pair. So usually it's shared, like you have so there's the Lewis structure for nitrogen. You have a hydrogen that comes along with its electron, a hydrogen that comes along with this electron, hydrogen with this electron. And it's electron from here and electron from here, they pair, and that's what makes this covalent bond. And now we have this pair here, and no electrons here. So what happens is this H plus comes on here, and both of these electrons become the bond between that, and then the whole thing is overall positive. My point is there's no more pairs of electrons from an H plus to come along and attack, which is why this can't be amphiprotic. It can give up that hydrogen, it can do this. It can do that. It can go back to being this, losing that. But it can't gain another electron, another hydrogen, another proton, I should say. Because all the pairs of electrons in its valence are used up. So you have to have a pair. The other one to pay attention to or look out for is oxygen. So I'll use H2O as the example. H3O is this positive. I know there's no such thing as H4O, but I'm going to give you that as an example in the test. This will help once we go over Bronsted-Lowry acids and bases have to do whether you accept an H plus or give up an H plus. The other definition of acids and bases is the Lewis acids and bases. And those are electron pair acceptors and electron pair donors. And that's what's going on here. And we're going to do that in the next chapter. It will make more sense probably by the end of this week. But one rule you can definitely go by for Bronsted-Lowry. If it doesn't have an H plus, it doesn't have hydrogen at all, there's no way it can be amphiprotic because it can't behave as an acid. All right, what about this one? Say it again.
It's not.
Yeah, right, it's not amphiprotic. Because it doesn't have a hydrogen anywhere to donate. And this is the example I was using before where this can turn into OH. And it can also turn into H3O plus. So that one's amphiprotic. So H2O can become OH and H plus, behaving like an acid. And here it is behaving like a base where it accepts an H plus. So that's the answer to this. I want to go back and see. It is like a little warm. I might get sick. Isn't it? It's a little warm. It's at least a little humid. Oh.
Yeah, it's humid, but less.
All right, yeah, that's kind of what I meant. Let me look at that dehumidifier real quick.
It's okay, the place is so we're going to be.
Um, which way does that shift if you decrease the temperature? Okay, but how do we think through it?
I just say positive goes to the products and
Okay,
then that's the reverse.
positive goes to the products, that's good. This is positive. But what you mean by positive goes to the products? this is positive, you go to the products, which means you want to go plus, you want to add it to the products. All right, if you decrease temperature, it's like I remove some heat, that means it's going to shift to the right. If you increase temperature, it'll shift it that way. Increase temperature, it'll shift away and go that direction. Decrease pressure. Do you remember what to do here? When it's pressure. Yes, but why?
Well, because when it's increasing pressure, you go to the spot as gas moves, and then
You go to
decrease the pressure, you go to the spot with the moves.
the more moles, you're right. So the first question, when it's about pressure, you can ignore this. This has nothing to do with pressure. And you go, how many moles of gas do we have? This is a gas, this is a gas, this is a gas. You'll know they're a gas if it has a G. How many moles of gas are on the left side? How many over here? There's 4. So if you decrease the pressure, that is, you lighten up the pressure so it can expand into a bigger space, so it'll shift that way. Increase the pressure, it'll shift to the left. And another way to ask this is if you decrease the volume, does that increase or decrease the pressure? If I increase it, these are together in a space, and let's say it's like a piston, where I can push down on the piston and decrease the space it's in, that will increase the pressure. If I decrease the volume, it increases the pressure, assuming there's not a valve letting gas come out. Gas, gas, two, if I decrease temperature, I like your mnemonic. If it's positive, heat goes with the products. But if it's negative, heat goes with the reactant. So that's negative. Instead of giving you this, I could say it's exothermic. See what I'm saying? If it's positive, I could say it's endothermic. All right, so if we decrease the temperature, which way does it shift? Think about, let's go back to just concentrations. Instead of thinking about temperature and pressure, if I remove a little bit of N2, which way does it shift? If I remove a little N2, did you say to the left? I don't know why I can't hear you. So if I remove a little bit, it'll shift towards it. If I remove a little bit of this, it'll shift towards it. If I add a little bit of this, it'll shift to the right. Add a little bit of this, it'll shift to the right. That's what this mnemonic is doing for you. Increasing temperature is like increasing the heat. Decreasing temperature is like removing some heat. So if I decrease the temperature, it heats on the left side. Which way does it shift? To the left. Decrease the temperature, that means remove some heat. That means it's going to shift to the left. If you increase the temperature, that'll shift it to the right.
Wait, but I thought if those agents positive, it goes to the products, and then it's reversed when you decrease the temperature. So if you increase the temperature,
In deciding which way it shifts by increasing or decreasing depends on which side you write the heat on.
so if the heat's originally on the reactant side, and then it goes to the products if you decrease the temperature?
No, it's the opposite. Did you say on the product side?
Like the delta H negative 181 would start on the reactant side, and then if you decrease the temperature, it goes to the products.
The negative tells you you write heat on the left side.
So then it goes to the products if you
And then you forget about this and you go, okay, now if I add the heat, it shifts that way. If I remove heat, it shifts this way. I mean, think of it in stages. Once you decide which side the heat goes on, you write in the heat and you forget all that. And then your logic just flows from there. Increase heat, that is temperature, shift that way. Decrease temperature, shift this way. You guys okay with that? This is a review. You guys follow this? And then for this one, decrease. All right, for this one, decrease the pressure. Decrease, increase the pressure. What's the first question you ask before you can answer it? Huh? Come on, you guys know this. Now we're on pressure. What do you look
No
at?
change.
Correct. No change. You got 2 moles of gas over here, 2 moles of gas over here. If they're equal, you get no change. We're shifting it. Anything else you want to review in here?
The concentration change,
This one, predict direction.
the initial concentration, I think it's that one. Like where you like if you add this, if you increase the protein. I think it's concentration change.
Okay, this one says increase H2 a little bit, or however much. And then you go back to equilibrium. All right. And let's assume this is a bar graph that tells you how much of each of these that exists. And I'm just making them up. If I increase H2 a little bit, so this would increase just a little bit, And then to get back to equilibrium, this will decrease. So if this decreases, what happens to this? The amount of this decreases a little bit if I have this here.
Decreases.
It decreases. You have to have these react together and combine to get over here. So if I increase this and then it starts to decrease, this will decrease. I'll lose that. And what happens over here?
Increases.
Increases. Plus, you increase the H2. This is the only one that's kind of tricky, but it's still kind of simple. You increase the H2, and then it goes back to equilibrium, so it's going to lose some as it goes back to equilibrium, but it always retains just a little bit extra after you do that. So you're sitting there at equilibrium, you add a little bit of H2, it shifts this way a little bit, but the H2, by the time it goes down a bit, it still has a little more than it originally had. It does go down. What you added, some of what you added starts to go down to go back this direction. You end up with a little bit left over. You guys follow that? If it's flowing this way in general, this is increasing and these are decreasing. Let's just stick with the same one. What if I increased CO and then we go back to equilibrium? So once you get back to equilibrium, do you have more or less over here? More. You have more or less here. Just a little bit more, because I added a little bit. And this, I add a little bit of this, and then this goes down to shift that way. What's happening to this is it shifts that way, it goes down. So this goes down. And then the other way, another thing I can say is CH3OH. If I suddenly increase this, and then it goes back to equilibrium, do I have more of this or less of this than I started with? It increases just a little bit. You add some of it, but then it removes as it goes back to equilibrium. But it doesn't go all the way back down to where it belongs. It's close. And what happens to these? If it's shifting this way, both of those are increasing. And I can't increase here the whole time. We could say decrease. What if I decreased H2? And then it goes back to equilibrium. Where do they stand after that? So if I remove a little H2, it's going to flow this way. This will still be a little bit less than it started at. What happens to this if it flows this way? Increases. And what happens to this if it flows this way? Decreases. So we said. The only weird one is the one that we're changing. But it ends up, like if I decrease this and then it goes back to equilibrium, it will end up a little bit lower than it started. It will end up a little bit decreased. But the other ones, if it's going this way, the idea is if I remove this, we flow this way. If I add this, we flow this way. If I remove this, we flow towards it. If I add this, we flow away from it. But the one you're changing is the only weird one. The other one should be obvious based on which way we're flowing. So. CH3OH. If I decrease a little CH3OH, which way does it flow?
Right.
To the right. If I remove some of this, it flows towards it. And what happens to these? They decrease because we're flowing that way. Since I decrease this, though, where does that one end up? Slightly decreased when it gets back to equilibrium. Another key here is the equilibrium point where K is. Anywhere along the line, we call it Q, the reaction quotient. And at some specific point, we call it K because that's where equilibrium is. So we change the concentration, we kick it away from equilibrium, and then it goes back to where the K is. And the numerical calculations are in the quizzes as well. But when you're changing pressure and temperature, you literally shift where K is. Okay, so when we're talking about shifting to the right or to the left, we're literally talking about shifting the equilibrium point when we change pressure and when we change temperature. At a higher temperature, you have a different equilibrium point. At a higher pressure, you have a different equilibrium point. If you don't change temperature and pressure, the K stays at the same spot. So you change it and then it flows back towards it. So you're actually changing K, the equilibrium constant, when you change temperature and pressure. Temperature or pressure. Anything else? All right. I'll encourage you to start going over these. We are going to cover a little more, so I'm going to add to it before we take a test. So you're back from break, get your brain back in gear. I'm doing the same thing. I literally barely worked last week, so I'm just now recovering and getting back together. So go over these. If you've got questions, we can go over it in class. Otherwise, I'm going to go on with what was next. pH is probably what I'll do next. Oh, yeah. More on that over break, too. I'll give you plenty of minutes before we'll soon. Yep, you too. You too.
keep talking, and then people just packed up and left, so.
Oh, really?
Alright, that's all we want back now, but I'm gonna do some more of this.
Oh. That's rough. No, I was gonna like do some other stuff and what? I was gonna.
Me too.
How do I stand? I have no,
Huh?
I know that.